Hi, it's Double O Pi, your undercover chemist here. Today we're going to be talking about oxidation reduction reactions, also known as redox reactions, and how to assign oxidation numbers to understand what's going on in those redox reactions. Very simply, a redox reaction, or oxidation reduction reaction, is a reaction in which electrons are transferred from one atom to another. And they're called oxidation reduction reactions because there are two different processes going on during that electron transfer. One atom is losing the electron, the other atom is gaining that electron. In general, electrons do not come off an atom and just float around by themselves. Instead, they move directly from one substance to another. And so there are always both of these processes going on. We have the process of losing the electron. So the atom which loses the electron will become more positively charged, and we call that process oxidation. Then we have the atom which is gaining the electron. Getting an extra negatively charged electron is going to make you more negatively charged, and we call that process reduction. Some people get confused as to which process is which. There are a couple of different ways you can remember. One is with a mnemonic. There are several of these, but the one that I like the best is Leo says grr. So remember there are two processes. One is Leo, so you can think of that as a lion, and the second we'll call grr, because that's pretty much what lions say. And so Leo stands for losing an electron is oxidation. Grr stands for gaining an electron is reduction. There are other mnemonics out there, and quite honestly, I don't use any of them because my brain doesn't work with mnemonics. So here's the way I remember. I remember a simple mathematical principle. Before I was just showing you these random circles, so let's pretend these atoms which are losing or gaining the electron actually have charges. So at the start of your reaction, your blue atom, whatever that happens to be, has a +2 charge, and your red atom, whatever element that happens to be, has a +3 charge. So as your blue atom loses an electron, it's going to become more positive. Its charge is going to change from +2 to +3. So it's increasing. Your red atom is gaining an electron. That's going to change the charge from +3 to +2. We said earlier the charge becomes more negative, but another way to think of that is it's becoming less positive. Or you could say it's becoming smaller. That charge is being reduced. And that's actually where the term reduction comes from. We'll talk later about where the term oxidation comes from. So, talking about which substance is oxidized and which is reduced is one way that we talk about the substances in a redox reaction. But there's another way that we talk about these substances, and that involves looking at these substances from a completely different point of view. So, when something undergoes oxidation, it is losing an electron, and that's the way we've been talking about it up till now. But that electron is not just disappearing into the ether. That electron is being transferred to the other atom that's involved. So not only is that blue atom losing its electron, it's giving it to the red atom. Without that giving of the electron, the red atom would not undergo reduction. So essentially what's happening here is the blue atom is facilitating the reduction that's happening on the red atom. It is the reducing agent, or sometimes we call it simply the reductant. So it is the substance that causes reduction to happen in the other substance. And of course, we can look at the red atom the same way. This substance is gaining an electron, but it only gains that electron because it takes the electron from the blue atom. Without the red atom taking the electron from the blue atom would never undergo oxidation. So this substance that gains the electron is called the oxidizing agent, or sometimes the oxidant. It is what causes oxidation to happen in the other substance. So we have a substance which is undergoing oxidation, which is also the reducing agent because it causes the other thing to be reduced. We have a substance undergoing reduction, which is also the oxidizing agent because it causes the other substance to be oxidized. Let's look at a very simple redox reaction. Here we have iron and copper reacting with each other. So you can see at the start of the reaction, we have iron 3 plus reacting with copper plus. And at the end of the reaction, we have iron 2 plus and copper 2 plus. So you can see right away this is a redox reaction because the charges on the molecules involved are changing, right? Look at iron. Iron is going from a +3 charge to a +2 charge. Its charge over the course of the reaction is getting smaller or less positive. In other words, that number, that charge, is being reduced. So iron is undergoing reduction. Iron is being reduced. Let's look at copper. Copper starts with a +1 charge and ends with a +2 charge. So its charge is actually getting bigger. It's becoming more positive. And that tells us that it is undergoing oxidation. Copper is being oxidized. So iron is undergoing reduction. It's the oxidizing agent, which causes copper to be oxidized. Copper is being oxidized. It gives its electron to iron. So it's the reducing agent that helps iron to be reduced. Here's a redox reaction. Most people look at this reaction and they don't even realize that it's a redox reaction because all of these molecules are neutral molecules. They all have a 0 charge. So how can electrons be transferred? Now, you'll notice, if you look carefully, this reaction is not balanced, and that's okay. We haven't started talking about balancing redox reactions, and so we're not even going to balance this because we don't need to have a balanced reaction to figure out what's being oxidized and what's being reduced. In order to figure out what's oxidized, what's reduced, or what's the oxidizing agent, what's the reducing agent, what we need is a little accounting trick, and we call that accounting trick an oxidation number. To calculate an oxidation number, we are going to pretend that everything in the world is made up of ionic compounds. And if that weren't the case, if everything were made up of ionic compounds, what would the charge on those ions be? There are some rules that help us understand what those charges would be. Here are the oxidation number rules. I'm going to give you a longer version, and then I'm going to compress it and abbreviate it so we can squish everything off to the side, and we'll talk about how to implement those oxidation number rules. The first rule is that oxidation numbers must add up to the charge on the molecule. So this is very easy to see if you look at a couple of different single atom molecules. We have iron 2 plus that has a +2 charge, and therefore the oxidation number must be +2. We have argon. You don't see a charge on argon because its charge is 0. Well, the oxidation number on that atom must add up to 0, so it's 0. The second rule is that all the atoms of free elements have a charge of 0. Now, a free element is any molecule composed of only one element. So here are a couple of free elements. Again, we have argon. We already know that argon has an oxidation number of 0. But if you look at nitrogen, nitrogen has 2 atoms of nitrogen in a molecule of nitrogen gas. Well, that doesn't matter because it's still just nitrogen bonded to itself, so it must also have an oxidation number of 0. Our third rule has to do with some metals. Basically, any metal in group 1A, and those are all your alkali metals, all of those metals are going to have a +1 charge. Any of your metals in group 2A, those are your alkaline earths, are going to have a +2 charge. And if you have aluminum, that will have a +3 charge. So here's an example of how we can use that to determine oxidation numbers. Here's an ionic compound, lithium chloride. Lithium, we know, has a +1 charge because of rule 3. What does that tell us about chlorine? Well, we know from rule 1 that the oxidation number on this molecule has to add up to 0. So the oxidation number of lithium plus the oxidation number of chlorine together must add up to 0. Lithium is +1. What is chlorine? Chlorine would have to be -1. Our fourth rule tells us that hydrogen has a +1 charge and fluorine has a -1 charge. So here's how we might use that. Here's carbon tetrafluoride. We know that fluorine is going to have a -1 charge. And we also know that the oxidation numbers on this molecule are going to add up to 0 because it's a neutral molecule. So carbon plus 4 fluorines each with a charge of -1 must add up to 0. So this is something that people sometimes forget, is that when you have more than one atom, each one of those atoms would have an oxidation number associated with it. So 4 fluorines, each -1 charge, plus carbon must equal 0. Carbon has to be +4. Rule 5, oxygen has a -2 charge. So we can look at this iron oxide. The charge on this molecule is 0. The charge on the oxygen is -2. We have 2 times the oxidation number of whatever iron is, plus 3 times oxygen, which is -2, has to equal 0. Okay, so that means 2 irons plus -6 are going to equal 0. And what we end up with when we do the algebra is that iron has a +3 oxidation number. Our sixth rule tells us that all of our group 7A elements, or halogens, have a -1 charge. Here's phosphorus pentachloride. It's a neutral molecule, so everything is going to have to add up to 0. The charge on chlorine is -1. So whatever that oxidation number for phosphorus is, if we add it to 5 chlorines, 5 times -1 has to add up to 0. The oxidation number of phosphorus must be +5. The seventh rule is that the elements in group 6A have a -2 charge. So carbon disulfide, we know that this is a neutral molecule, and again the charge on sulfur is -2 because that's a group 6 element. The oxidation numbers must add up to 0 because it's a neutral molecule. Carbon plus 2 sulfurs, carbon plus 2 times -2 is going to equal 0. That tells us carbon has to have a +4 oxidation number. Our last rule tells us that the elements in group 5A have a -3 charge. So for example, here's HCN, and you can see that even though this has 3 different elements, which we've never done before, it works just like it did when we have 2 elements. So we know that nitrogen has a -3 because nitrogen's a group 5A atom. And for rule 4, hydrogen must have a +1 charge. And then let's do our math. This is a neutral molecule. Everything adds up to 0. Hydrogen, carbon, nitrogen oxidation numbers must add up to 0. So +1 plus something plus -3 equals 0. Carbon must have a +2 charge. As we went through this, you probably noticed some strange things. For example, rule 4, fluorine equals -1. And rule 6, group 7A equals -1. Oh, that's kind of strange, right? Fluorine isn't group 7A. Fluorine's a halogen. Why would we have these rules that duplicate each other? The answer is that there's an unwritten rule that if you have a conflict between the 2 rules, you're going to pick the rule that comes first in the list. So you notice that all of these rules have numbers. There's a reason for that. Let's look at an example. Here's fluorine gas, F2. What oxidation number rules should we use for this molecule? Now, there are actually a couple of different rules that talk about fluorine. Right? Here's one. Fluorine is -1. But this is also a free element. This is a molecule with just fluorine. And so that's the rule that we're going to pick. Free elements have an oxidation number of 0. So that tells us that our oxidation number for fluorine is going to be 0. And this actually makes sense because our very first rule tells us that the oxidation numbers of the atoms within a molecule have to add up to the charge on the molecule. If fluorine had a -1 charge, and you had 2 of them, the charge on this molecule would have to be -2. But it's not, it's 0. Okay, here's another one. Lithium hydride. We have a couple of different rules that might apply here. Lithium is a group 1A element. It's an alkali metal, so lithium could have a +1 charge. Hydrogen also could have a +1 charge, but if you did that, you'd have +1 and +1, and that would add up to +2. This isn't a +2 molecule. It's a neutral molecule. So rule 1 has to come into play. What do we have? We're going to pick this to tell us what the charge is. The rule about lithium comes before the rule about hydrogen. So lithium must have a +1 charge. Hydrogen must have a -1 charge. How about FCl? If we just look at our list, we see that both of those are halogens and should have a -1 charge, except, oh, if we did that, the molecule would have a -2 charge, and it doesn't. Okay, what do we have? Well, there's this other rule that says fluorine has a -1 charge. That comes before the group 7A rule. That's the rule we're going to apply. Fluorine has a -1 charge. Chlorine must have a +1 charge. So let's now take this and go back to the confusing redox reaction we were looking at the beginning. Methane and oxygen making carbon dioxide and water. We could not see before what was being oxidized or what was being reduced, so we're going to use our oxidation rules to find out. Here are the rules, and here's our reaction. Let's go through these molecules one at a time, starting with methane. What rule are we going to apply to figure out what's going on? First of all, when you see carbon, there are no rules about carbon, so look for the other atoms. Okay, here's what we have. We have hydrogen being +1. Carbon plus 4 hydrogens have to be 0 because this is a neutral molecule. If hydrogen's +1, carbon must have a -4 charge. Now let's look at oxygen. What's the oxidation number on oxygen? We could use the rule that says oxygen has a -2 charge, but a better rule to use might be the rule that says free elements have an oxidation number of 0. That's higher up the list. And so that's the one we're going to pick. Oxygen has a charge of 0. Let's move to the other side of the reaction and look at carbon dioxide. Once again, we have carbon, and we know there are no carbon rules, so let's pick on oxygen here. Oxygen has a -2 charge. Carbon plus 2 oxygens must equal 0 because it's a neutral molecule. And if you do the math, you figure out that carbon must have a +4 charge. The last molecule is water. Now, we have hydrogen here and we have oxygen, and we know we have rules for both. So here are 2 rules. The hydrogen rule wins. But as it turns out, oxygen is still -2 when you do the math. So here are the oxidation numbers for every atom in every molecule of this reaction. Now let's look at what's changing, what is being oxidized, and what is being reduced. Start with a hydrogen. Hydrogen has +1 charge on the left side of the equation, and it also has a +1 charge on the right side of the equation. So hydrogen is actually not gaining or losing electrons. How about carbon? Carbon starts at a -4 and it ends at a +4. So carbon has become more positive. Carbon is being oxidized. If you look at oxygen, oxygen starts at 0. And this is a little confusing because we have oxygen in 2 different places. But if you look at both of these oxygens on the right side, both of them have an oxidation number of -2. So oxygen is being reduced. Oxygen is the oxidizing agent that helps oxidize carbon. And in fact, this is where the term oxidation comes from, because when oxygen acts on other atoms, it frequently serves as the oxidizing agent. And so the process of oxidation is named for oxygen, which is a very frequent oxidizing agent. Thank you for watching this video. If you liked it, check out all the other videos on the Double O Pi YouTube channel. In our next video, we're going to look at how to balance a redox reaction.